Okay, so this was the question actually. I think we left here only, isn't it? I think so. I am audible, I think, huh?
Yes,
Yes,
sir.
sir.
Okay. So this was the question. You can see here. We were asked to calculate the mass in kg for hydrogen gas. The temperature of thermometer is 83 degrees Celsius. Pressure gauge reading is 20 bars. Cylindrical container diameter is 20 centimeter. Length is 150 centimeter. Okay. So now basically, what we have to do, we have to calculate the mass, and we have to use the equation PV is equal to MRT. Okay, this is the equation we have to use actually. Now the one question which somebody asked was, shall we go for 20 bar? Okay, or we should take the absolute pressure. This is the gauge pressure. Okay, this is the gauge pressure, and shall we take absolute pressure or shall we go for gauge pressure? Okay, now the thing is, suppose if I am having this particular container and the gauge shows here a pressure which is equal to 0, then what is the pressure inside the container?
Atmospheric pressure.
Atmospheric
One
pressure.
ATM.
It is atmospheric pressure. So would hydrogen be there inside the container or not?
Yes, sir.
It would be there. So that means when the pressure is atmospheric, the hydrogen would be there. And there is a pressure of the gauge which is showing 20 bar. So in totality, you can say the total pressure is 21 bar. So we have to calculate the mass of the hydrogen for 21 bar, not for 20 bar. Because at 1 bar also,
Sir, 21 bar. Why, sir? ATM, 1 ATM pressure we have, right?
see, I am just giving you an example. Actually, I will be taking the exact value when I will be solving it. Okay. So let us see now. So we have to go for 20 bar plus 1 ATM. Okay. That would be 21.01325 bar. Okay. So let us see how we are going to solve it. Now this is once again, I have written this question. So you can see, we can use this particular equation. You already know about it. Okay. And then this is the relationship for the mass. So first of all, let us calculate the various parameters or the physical properties which are involved here: pressure, volume, R, and T. So absolute pressure is given by atmospheric pressure plus gauge pressure. So 20 plus 1.01325 bar, that gives us 21.01325 bar. That is the total pressure inside the container. Then if I convert this value in kilopascals, then I will have to multiply this value by 10 raised to power 2. So it gives the pressure as 21.01325 into 10 raised to power 2 kilopascals. So I hope this part is clear to you. So we have calculated the pressure now. Now let us go to the second part, which is the volume. I know what is the volume. Volume is pi by 4 d square into L. This is a cylindrical vessel, so this will be the volume. So you can put the values. So 22 by 7 divided by 4. This is the diameter, 0.2 into 0.2. You can see the diameter is 20 centimeter. So you can divide here by 100. That will give you the value in meters actually. I think somebody is trying to join. Just wait for a minute. Yes. Devansh, you are joining late actually. You should have joined earlier. Okay. Then there is one more student. Okay. This creates a problem. Today I am allowing you people to join after 1:10 actually. From next time I am telling all of you, you should join by 1:05. Otherwise it wastes my time and your time also. Okay. So now you can see I have taken the value of diameter into in meters here, and 1.5 meter is the length here. 150 centimeter converting into meters is 1.5 meter, and this is the value of the volume. This is what I get. So you can cross check. If it is wrong, you can tell me. The third part is the characteristic gas constant R. So R stands for characteristic gas constant, and its value is equal to universal gas constant divided by the uh, molecular weight of the hydrogen. So you can see it here. This is the value, and you can see the final units. Kilomole and kilomole cancels out, so we are left with the units kilojoule per kg Kelvin. So unit system is very important for you to understand, because if you are using the wrong units, you won't be able to get the correct answer. Then when I go for the temperature is 83 degrees Celsius, but in this equation we will have to take it in kelvins. So I add here 273.15 and get the value in the of the temperature in kelvins, which is 356.15. So I have calculated the pressure, volume, R and T. Now I put all the values and final answer comes out to be this 0.06688. So this value, pressure is in kilopascals, okay, volume is in meter cubes, then this value is the value of R, and this is the unit, kilojoules per kg Kelvin, and here the temperature is in Kelvin. So I have chosen this particular set of the units, and then I have got the value of mass in kgs actually. Okay, so it is 66.88 grams. So those who are getting 66.88 grams, their answer is correct. All other answers are incorrect. Now I would like to discuss about the unit system actually. Why I have chosen this particular set of the units. Now you see it. This is the formula for the mass of the gas. PV is equal to mRT. So mass is PV by RT. Now let us check these units. What are the units? Pressure I have taken kilopascal. Volume in taken meter cube. This is the unit of R, and this is the unit of temperature. So you can see Pascal, if I calculate, this is actually Newton per meter square, and kilo is means its prefix. It is just showing the value is 10 raised to power 3. We are using it for 10 raised to power 3. Then this is the value of volume. In denominator also it is kilo, and joule. If I take joule is actually Newton meter. So I have written that value Newton meter per kg per Kelvin and multiplied here by Kelvin. Now you can see here, if I just a minute, you can see here the Newton and Newton will cancel out. Okay, this meter square and this meter will cancel out. This Kelvin and Kelvin will cancel out. This meter will cancel out with this meter. So we are only left with this kgs. So this kgs will go up here, and we will get the value of mass in kgs. So basically I have considered a consistent set of the units, and this consistent set of units is comprising of pressure is taken in kilopascal, volume has been taken in meter cubes, temperature is in Kelvin, and the value of R is in kilojoules per kg per Kelvin. So this is the consistent set of the units. So actually, when you take these units, the final value of the mass will come out to be in kilograms. So you consider if the mass is given to you in kilograms and you are asked to calculate the pressure. Okay, if you are asked to calculate the pressure, so if you take all other values in this consistent set of units, then the pressure will come out to be in kilopascal. So you should always remember, it is not necessary that you take this particular set of the units. It is up to you to train your mind according to which you can use different set of the units also. I'm not forcing you to use this particular set of the consistent units, but you should be aware which set of the units you should go for, so that the final answer is correct actually. So I hope this part is clear to you. Is it?
Yes, sir. And
Sir,
sir,
as in the as
Yes.
in this
Yes.
sir, about rounding of the certain values, for how much can we round off the value, like 21.01325? It is, then can we write it as just 21.01?
See, actually, once you know the exact value, for the moment you can use the exact value, and what you can do is later on, if you see this particular value of the mass, it is coming out to be 0.06688. So you can round it off to 67 grams also. Okay, it is as good as 67 grams, so it doesn't matter. But actually, initially you should remember these values. Okay,
Okay, sir.
rounding off. See, basically, when you are going to be engineers, so tomorrow, if you are going in the industry, there the smaller things also matter a lot to us. For example, if you have to launch a rocket, and if you will see there, there you will have to go for maybe up to 100 decimals values, because if you are rounding off there, it may lead to some a lot of errors actually. Okay, so you have to see how much error is means can be tolerated in a particular application, only then only according to that you have to round it off. Okay.
Okay, sir.
Okay.
So like
Let us-
in this question, calculations were quite tough. So are we used to allow use calculators during exams?
yes, you are allowed to use calculators. There is no question that you won't be allowed. You are allowed. The calculator is a must in engineering classes. Okay, and you should purchase if you have not, but it should not be programmable calculator. Okay. For the moment, actually, your exams will be conducted online. During these online exams, you can use your mobile phones also. That's not a means you have a choice for that. But when you will be appearing for the offline classes, offline examination, there you should have a calculator which is not programmable. Okay. Okay.
Okay, sir.
So this is the chapter on basic of the thermodynamics. Now we are proceeding to what you have. One more thing, what you have to do is whatever is the numerical problems related to the topics which I have taught you, you can do that from the exercise also. You know which book is to be followed. See, you have to follow a book on basic thermodynamics by P.K. Nag. So the book is, just a minute. The name of the book is P.K. Nag. Basic thermodynamics. Basic thermodynamics by P.K. Nag. Can you hear me?
Yes, sir.
Yes,
Okay.
Yes, sir.
So if you do you have a copy of this book? Have you purchased it or not?
Not yet, sir.
Sir,
Okay,
we
what I
have
will
PDF. We have the
what
PDF.
okay, you have the PDF, so you can circulate it on the group actually. Okay, so that everybody can be benefited from this, because there may be many students who may not be going out or may not be purchasing right now. So you can send a copy of that on the PDF on your group actually, or you can share. Otherwise, I also have a copy. Whatever the would be the required things, I will forward it to you on the group. Okay. Now this is now the second chapter actually. This is on temperature, and the most important thing in this chapter is the zeroth law of thermodynamics. I hope you must have studied it, but I am repeating it here. What is the zeroth law of thermodynamics? When body A is in thermal equilibrium with body B and also separately with body C, then body C and B will also be in thermal equilibrium with each other. And this is known as the zeroth law of thermodynamics, and it forms the basis for the temperature measurement. So simply, if you will see this particular diagram, you can understand that suppose we have this particular body A and its temperature is TA. Okay, and this is in thermal equilibrium with body B. So body B is kept here, but they are in thermal equilibrium. They are means attached by some medium actually, so that if they are in thermal means they are in communication with each other, so the temperature of body A and temperature of body B will be same. So this is written here, TA is equal to TB. And now what I do is I say that body C is also in thermal equilibrium with body A, but not in thermal equilibrium with but not in communication with body C. Okay, so the communication between body A and B is there, and communication is there between body A and C. Means when I say communication, means thermal communication basically. So what will happen in this particular case? TA will also be equal to TC. So you can see the left hand side of both these equation we have TA, and the right hand side we have TB and TC. So it means if TA is equal to TB and TA is also equal to TC, then TB should also be equal to TC. So this is the zeroth law of thermodynamics, very simple, and it forms the basis for the measurement of the temperature. So basically, zeroth law of thermodynamics gives a property. It gives rise to a property which is actually known as temperature. So you should always remember this significance of the zeroth law of thermodynamics, because it gives rise to a property which is known as temperature. We have discussed about the various types of the properties earlier itself. Okay. Now let us come to the different temperature scales. So we are going to use mainly three types of the temperature scales. One is Celsius, Fahrenheit, and Kelvin. You know about all these, and the relationship between these temperature scales is given by the formula. Suppose it is degree Celsius, you have to subtract the freezing point of the water divided by boiling point of water minus freezing point of the water, and equate that equal to the Fahrenheit value minus freezing point of the water in Fahrenheit. So if I am taking here in Celsius, here I will take in freezing point in degree Celsius. Similarly, boiling point will be in degree Celsius on the left hand side. Okay, and here the boiling point will be in Fahrenheit. Here also it is in Fahrenheit. So now you see here, finally I can say that C degree C minus what is the freezing point of water in degree Celsius? It is 0 degree Celsius divided by boiling point of water is 100 minus freezing point of water 0. On Fahrenheit scale, the freezing point of the water is 32 Fahrenheit and the boiling point is 212. So 212 minus 32. So this is the relationship between Celsius and Fahrenheit. So if you are given the temperature in Fahrenheit, you can convert that into Celsius. So finally, this is the relationship. Degree Celsius divided by 100 is equal to Fahrenheit minus 32 divided by 180. So you can convert Fahrenheit into Celsius and Celsius into Fahrenheit using this particular relationship. Here you can divide also, it becomes 5, it becomes 9. In a similar manner, I can go for the relationship between Celsius and Kelvin. So let us see. So degree Celsius, so when we will be subtracting 0, it will be degree Celsius only divided by 100. This is Kelvin. On Kelvin scale, the freezing point of water is 273.15. Boiling point is 373.15. This is the freezing point. And finally, we get this particular expression. So 100 and 100 cancels out, and we can get the value of degree Celsius is equal to Kelvin minus 273.15. And we can club these two equations, means Celsius, Fahrenheit, and Kelvin. And finally, this is the relationship that we get. We can convert any temperature given in Fahrenheit into Celsius or Kelvin, and vice versa. This we can do. If we can also cancel some of the values in the denominator, and we will get finally this particular expression. So you need to know how to convert Celsius into Fahrenheit and Fahrenheit into Kelvin. But mainly when we are using, when we are studying this particular case, mostly you will have to convert Celsius into Kelvin. Mostly we will be using this particular thing only. Okay, Celsius into Kelvin. Fahrenheit is normally not used because it is FPS system of units, and FPS system of units is not used here in India. We are only using the SI system of the units. Okay. Now this is a question. So what you can do is, I'm not solving this particular question. I'm just leaving it for you people. What you can do when I will be loading the, you can say, lecture on the YouTube, then you can see this question and solve it. It's a simple question where we have to calculate the pressure, and the pressure is equal to rho GH. Okay, you just try this question. If you have any problem, you can ask me. Okay, here I have also given the solution. So better you can see it yourself. If you have any problem, you can ask me later on. Now this is, so basically till now we have completed chapter number 1. In chapter number 2, I was just to tell you what is the zeroth law of thermodynamics and what are the various temperature scales. So now we are going towards chapter number 3. Okay, this is chapter number 3. Chapter number 1 is over. Chapter number 2, whatever I wanted to tell you, I have told you. Now this is a very important chapter, work and heat transfer. Now let us discuss about it. A closed system and its surroundings can interact in two ways. And what are those two ways? One is by work transfer and another is by heat transfer. These may be called energy interactions, and these bring about changes in the properties of the system. So you know it, suppose you have a closed system, suppose you have a vessel which is containing a particular gas. If you heat it, what will happen? Its temperature will increase, because in that particular case the volume of the vessel will be constant. So if you are heating it, its temperature will increase. When the temperature will increase, the pressure of the gas will also increase. So that is why we say that these are the energy interactions which bring about changes in the properties of the system. Now thermodynamics mainly studies these energy interactions and the associated property changes in the system. Okay, so this is the definition of the thermodynamics. I told you this in the first class of the thermodynamics. Now, in thermodynamics, work is considered as occurring between the system and its surroundings. So, this is very, very important. Work transfer is considered as occurring between the system and the surroundings. When I say this particular line, it means work is observed when it crosses the system boundary. Okay, if this is the system, if I take this as the closed system, okay, and if the work is either going crossing the system from the this is the system and this is the surrounding, so if the direction is if the work is starting here and going out, only then we can say it is the work transfer. Otherwise we will not say it as a work transfer. You should focus here, work transfer. Transfer, it is very, very important word here. You won't call it as only work, or you won't call it as only heat. It is heat transfer and work transfer always. Okay, now this is the definition of the thermodynamic work. Actually, in physics, you know, when we talk about the work, you say that W is equal to F dot S, where F is the force and S is the displacement, and their dot product give you the work. But in thermodynamics, the definition is different. Here we say work is said to be done by a system if the sole effect on things external to the system can be reduced to that of raising a weight. Okay, once again I will read this definition. Work is said to be done by a system if the sole effect on things external to the system can be reduced to that of raising a weight. So that means whatever is the effect this work is going to do, with the help of that effect, if we can raise the weight, then only we can say that work is done by the system. Okay, now the next thing, this is also very important. The weight may not actually be raised, but the net effect external to the system would be that of raising a weight. So in the next slide you will see how we are going to justify this particular definition. Now you focus it here. Now what you can see here on the left hand side diagram, you have a battery here. It has two terminals, positive and negative terminals, and with these terminals we have attached a motor, and with this shaft of the motor, okay, this is the shaft of the motor, we have attached a fan. So basically this fan is driven by the motor, and the motor is getting the energy from the battery, and this fan is existing outside the system boundary. Where is the boundary? Boundary is here. You can see within the boundary you have the battery and you have the motor, but the fan is in the surroundings. So can we make some change in this particular system so that we can find out that this system is doing work? Actually this system is doing work. There is work transfer because there is the motion of the shaft actually, and this motion of the shaft can be converted into raising a weight. You can see here in the right hand side diagram. So what we have done, we have removed this fan. This fan have been removed, and in place of that we have installed a pulley. So when we have installed a pulley, and when this motor moves, its shaft rotates. When this shaft will rotate, and there is a rope over this pulley, and at the end of the rope there is a weight. So when this shaft will rotate, the pulley will rotate, and it will screw this, you can say the rope will be lifted up. When the rope will be lifted up, the weight will also be lifted up. So that is what is the definition of the work transfer in case of a thermodynamics. Okay, so what we have done, we have converted a battery and motor system to which is comprising of battery, motor and fan, into a battery, motor and pulley, and this pulley is able to raise the weight. See, we never take lowering of the weight, because lowering of weight can occur because of the weight of the mass of the weight also, okay, or because of the motion of the body itself. So we don't take that lowering down of the weight as a work transfer. So raising of a weight has been done in this particular case. So we have reduced the system in such a manner that the weight has been lifted up. So we say that the work transfer is taking place. Now, one very important thing now here, when work is done by a system, it is arbitrarily taken as positive, and when work is done on the system, it is taken to be negative. So you can see this is the system and the work is moving out of the system. So this is positive for us. So when the system is doing work, then it is positive. When means the system is doing work on the surroundings. And when the surroundings are doing work on the system, then it is negative. But you should always uh, remember it, but not from system to surrounding or from surrounding to system. Rather, it is work done by the system, it is positive, and work done on the system, it is negative. So these are the two terminologies which we will be using. So work done by the system is positive and work done on the system is negative, and we will be using a symbol W for this particular case. Now let us discuss about various types of the work. This is the first type of the work. It is actually PDV work or displacement work in a simple compressible system. So you should try to understand the terminology here. It is a PDV work, also known as displacement work in a simple compressible system. Now, what is the meaning of the simple compressible system? Simple compressible system basically comprises of a, you can say, a piston and cylinder arrangement. This is the example of the simple compressible system. Otherwise, what you can do, if you have a balloon, it's also a closed system. So balloon can also be compressed or can be expanded. So that is also a simple compressible system. Okay. So there is when we are talking about the PDV work or the displacement work in a simple compressible system, our focus is on a closed system where the boundary can be where the boundary is flexible actually. Okay. So in case of a piston cylinder arrangement, the boundary can be flexible, or if it is a balloon, there also the boundary can be flexible, because when we are filling air into the balloon, then it will be inflated. Okay. Similarly, the piston can move either inwards or outwards. So the boundary can vary. So you can see it here. What is given here? We have a piston cylinder arrangement here. This is the initial position of the piston. Okay. This is the point number 1. The pressure of the gas inside is P1, volume is V1. And one more thing, the gas has been considered as the system only. The boundary is shown here. This is the boundary. Okay, this is boundary. So boundary is only encompassing the gas. So gas is the system here, and its pressure is P1, volume is V1, and temperature can be T1. Now, due to some reason, if the piston moves outwards, you can see the motion of the piston is shown to be outwards. So it reaches up to this particular position, and now the pressure is P2 and the volume is V2, and the boundary being flexible has reached the new position. Now this is the boundary here. Okay, earlier it was here only. This is the initial position of the boundary. Now the final position of the boundary is up to this location. Okay. Now let us see this particular diagram actually. Now you can see here, I have shown both the positions here. This is position number 1 and this is position number 2. And what I have tried to show is, I have tried to plot these two positions of the gas on the PV diagram. So you can see here, this is the pressure P1 is here and the volume V1 is here. Here the pressure is, you can say here the pressure is P2 and the volume here is V2. Okay. And now what I consider is, I have considered some location here BB. At this location, when the piston is at this location BB, the pressure exerted by the gas is, let us say, P. Okay, this is the pressure exerted by the gas. Now what happens? Suppose this piston moves to the new location C, and the displacement is DL. And one more thing is, what I have written here is A is the cross-sectional area of the piston. So focus on 3 items only. One, at location BB, the pressure exerted by the piston is P. Due to this pressure, the piston moves to the new location and its displacement is dl, and the area of cross section of the piston is A. Now we want to calculate the displacement work actually, or the PdV work. Now one more thing, important thing that I would like to tell here is the process is quasi-static, that is all states are in quasi-static or quasi-equilibrium, that means almost equilibrium. So we know each and every state through which the system is passing. So that is the prerequisite when we are calculating the PdV work. So that is a required condition that the process has to be quasi-static. Okay. Now you see it here. Now what is the force which is acting on the piston actually? You can see this is the pressure which is acting at this particular location P. Area of the piston is A. So if I have to calculate the force on the piston, I can multiply pressure and area. So P into A gives me the force which is acting on the piston at this particular moment, at this point B, B or C, C. Okay, during this displacement, the pressure is P and the force is P into A. So you can see the units also. Pressure as the units Newton per meter square, area as the units meter square. So meter square and meter square will cancel out, and the value of the force will come out to be in newtons. Now during this motion from BB to CC, there is a very small work or infinitesimal work which is done by the piston, and that work can be given as F dot dl. F dot dl. And this infinitesimal work now I am representing as delta W. You should see it here. It is something like this, delta W. So it's a small work. I am not representing it as dW. I will tell you the reason why later on. For the timing, we are not going to use this dW. We will be using delta W. Okay, and this is equal to F into dl. Now this F can be replaced as pressure into area multiplied by dl, and this area into dl is nothing but small change in this volume of the gas, which is equal to dv. So delta W comes out to be equal to PdV, and I have written the reason here. A into dl is equal to dv. So we have this particular equation, delta W is equal to PdV, and this is the value of the PdV work or the displacement work in a simple compressible system. So this is the equation that we will be using a lot in this particular course. And then if we want to calculate the work for the complete process, because the process is taking place from state point 1 to state point 2. Okay, state point 1 to state point 2. So what we will have to do, we will have to integrate this above equation, this equation from 1 to 2. So this equation is to be integrated from 1 to 2. On the right hand side also I have kept this term PdV in integrals from 1 to 2, and this value on integration I write it as W1 to 2. It means this is the value of the work transfer. This is work transfer for process 1 to 2. So this is the exact nomenclature which you are going to use. So you have to write it in this fashion, W1 to 2, and it says that work transfer for the process 1 to 2, and this is the equation, final equation. Now let us focus here on the right hand side also on the diagram here. Okay, now what you can see here we have considered this particular location which is between B and C. So the pressure here was P actually. This is the change in the volume dV. Okay, and you can consider that this is a rectangular strip. So that is why we have saying that the area under this area under this strip is actually PdV. This is PdV. Okay, And if we have to calculate the total area, we will have to take the integrals from 1 to 2 for the whole process. That is how we have calculated the value of the displacement work or the PDV work. So it's quite simple. Now, there are some conditions for which this relationship is valid. Which relationship? W1 to 2 is equal to integral PDV. The above equation is valid for number 1, closed system. This I have already told you. Second is quasi-static process. And the third is when there is, I should write not pressure, it is external resistance at the boundary. External resistance at boundary. So can you tell me, is there any external resistance at the boundary? This is the question for you.
Yes, yes, sir. The atmospheric pressure.
Atmospheric pressure, yes. It is the atmospheric pressure which is acting on the boundary actually. You can see here in the diagram also. See, what is the external resistance? This is the P atmospheric which is acting here. Okay, so it is P atmospheric. So if this P atmospheric is now not there, then what would be the name of this particular process?
Sir,
Anyone?
Free expansion.
Yes, it would be free expansion. If there is no pressure, that means there would be vacuum actually. And in case if there is vacuum, then it will be free expansion. Okay. The expansion of a gas against vacuum is known as free expansion. So let us proceed further. Now we can use this particular equation. Which equation? Delta W is equal to PDV for various processes. Now, what are the various processes? The various processes which a simple compressible system or closed system can undergo are: the first one is the constant volume process, also known as isochoric. The second one is the constant pressure process, isobaric. Third is the constant temperature process, also known as isothermal process. Fourth is the reversible adiabatic process, represented by PV raised to power gamma is equal to constant. And the fifth one is the polytropic process, represented by PV raised to power n is equal to constant. When I say constant pressure process or isobaric process, there is another name also. It is actually isopistic process. Okay, isopistic process. Once again, I would like to tell you, if you see the serial number 4, I have written here reversible adiabatic process. But if I see the other names, constant volume process, constant pressure, constant temperature, or polytropic process, nowhere I have written reversible. Okay, but for your information, I would like to tell you, when I say constant volume process and I am calculating the PDV work, there is already the condition that it has to be quasi-static, and only a quasi-static process is a reversible process. So when I am saying constant volume process or isochoric process, even if I am not using reversible isochoric process or reversible constant volume process, it is mean to be same actually. So it is only reversible constant volume process or quasi-static constant volume process. So this you should always keep in mind. So all the remaining processes where I have not used reversible, they are deemed to be reversible. So they are quasi-static in nature actually. Only then we can use this particular equation of delta W, which is equal to PDV. Okay. Now let us proceed to the work calculation for a constant volume process. So you can see this is the PV diagram. So you can either show it by a vertical line going downwards or a vertical line which is going upward from 1 to 2 down here, or 1 to 2 upwards here. Okay. So in this particular case, if you calculate the value of PDV, delta W is equal to PDV. So to calculate the total work, I can integrate this equation from 1 to 2. So integrating both sides. Now what is the value of dV? Now you know the value of change in volume is 0. So in case of constant volume process, the work will come out to be 0. So W1 to 2 means the work done in case of process 1 to 2 will be 0. So whether it is going downwards, if the process is taking place from 1 to 2 downwards or from 1 to 2 upwards. That will not make any difference because there is no change in the volume during this particular process. V1 is equal to V2. So that is why the work transfer is equal to 0. And I have already told you, if we have to calculate the PDV work, it is the area under the curve. It is equal to the area under the curve, which is actually equal to PDV work. So this is PDV work. Okay. Here we have the pressure, here we have the volume. So this area gives us the PDV work. Now let us talk about the constant pressure or the isobaric process. It is isopistic also. So you can see either I can go from 1 to 2 this way, or I can go 1 to 2 this way. And in this case, you can see the pressure is constant. So P1 is equal to P2. Okay, P1 is equal to P2. You take any of these, P1 is equal to P2. So pressure is constant. So once again, what I can do is I can apply this particular equation. I can integrate both sides, delta W1 to 2, delta W PDV1 to 2, integral both sides. Now you see here, when I say isobaric process, this P is constant here. So I can take out this P from the integration sign. So I will be left with dV only. And I can integrate this particular value and I will get V here only, varying between 1 to 2. And this is the final expression PV2 minus P1. And here I have written it as PV2 minus PV1. Any questions till now? Any questions? Okay. So once again, I was here. Now I have the gas equation PV1 is equal to MRT1 and PV2 is equal to MRT2. Okay, this is the gas equation only which I am using. So PV1 is equal to MRT1. So that means I can replace PV2 by MRT2. So MRT2 here, and in place of PV1 I can use MRT1 here. So MR into T2 minus T1. So this is the value of the work transfer in case of isobaric process. W1 to 2 is equal to PV2 minus V1, which is equal to MR T2 minus T1. Now let us talk about the isothermal process. I know you have studied this part in the physics of 11th class also. So it's not difficult for you people. So here, isothermal process, when you take isothermal process, PV is equal to MRT. This value is constant. Now, if you will see here, MR is also already constant for a particular gas, and temperature is also constant. Okay, so the right hand side is in totality constant. So you are left with PV is equal to constant, or I can say P1 V1 is equal to P2 V2 is equal to P3 V3. All these are constant. And then this is the process, isothermal process. You can say it is temperature is equal to constant, or P into V is equal to constant. So I can use this particular equation here. Okay, I can integrate both sides from 1 to 2. So what I will get, you can see it here. If I have to calculate the value of P here, I have P into V is equal to constant. So P will come out to be C by V. So you can see it here. I have written here, the work transfer will be given by C dV by V. And reason I have written already here, PV is equal to constant and P is equal to C by V. Okay. So C can be taken out of the integration sign here. So you are left with C log V2 by V1. And then this value of C is either P1 V1 or P2 V2. So work is given by P1 V1 log V2 by V1 or P2 V2 log V2 by V1. Okay. Because this value P1 V1 and P2 V2, they are same actually. Then in place of this P1 V1, I can also write MRT1, MRT2. Both these I can write. Then I know that P1 V1 is equal to P2 V2. So V2 minus V2 by V1 is equal to P1 by P2. So what I have done is, in this particular equation, if I say this is equation number 1, the log term is V2 by V1. So log term V2 by V1 can be replaced by P1 by P2 here. So I will get the relationship W1 to 2 is equal to P1 V1 log P1 by P2, or P2 V2 log P1 by P2, or if I replace P1 V1 by MRT1, and here MRT2. So we have 8 expressions basically for the calculation of the work in case of isothermal process, and these 8 expressions, as you can see, are the first one is you can say P1 V1 log V2 by V1. I can replace this by P1 by P2. I can write here MRT1. I can write MRT2. I can write P2 V2. So whatever is given to you, you can write the expression according to that value. Now proceeding to the next process, it is reversible adiabatic process. So I know that you must be knowing this particular relationship, that in case of a reversible adiabatic process, PV raised to power gamma is equal to constant. Okay, this is already known to you. There are some other equations also I will write here. Those equations are TV raised to power gamma minus 1 is equal to constant. The color is not suitable, so I will take the red color. So TV raised to power gamma minus 1 is equal to constant. For you, I will tell you that gamma is nothing but ratio of specific heat Cp by Cv, and the value of gamma is equal to 1.67 equal to 1.4 equal to 1.33. This is for monoatomic gas, this is for diatomic gas, and this is for polyatomic gas. Okay, so we have different values of gamma. If we take air, for air the value of gamma is equal to 1.4. so you should always remember this, the value of gamma for the air, because mostly we will be using doing calculations for the air. Now what I have done here is I have drawn the PV diagram for reversible adiabatic process. So what is the meaning of the adiabatic? Adiabatic means no heat transfer. Okay, no heat transfer from the system to the surroundings or from the surrounding to the systems. तो इसका मतलब ये हुआ कि ना तो सिस्टम से हीट बाहर जा रही है या बाहर से अंदर आ रही है. Nothing is happening like that. So what I have shown here is I have shown if from 1 to 2, if this is 2 and this is 1, initial state is same in both the cases, and this process is constant temperature process, then a then a adiabatic process, reversible adiabatic process, has higher slope in comparison to constant temperature process. So that is why this is the diagram for the reversible adiabatic process. PV raised
Sir,
to
I
power
did
gamma.
not understand.
This you will understand later on. Okay, the few next topics, maybe in the next class or next class, I will be telling you why the constant temperature is here and the reversible adiabatic is here. When I will be talking about the slope, about the value, some other things I will be talking about, then you will be able to understand it. Okay, for the moment you can say that you can think that constant temperature is here and the PV raised to power gamma is here. Okay, so once again I have to use this particular equation, delta W is equal to PdV, integrating both the sides, and we have to replace this P. Okay, we have to replace this P and to integrate it. So this is the relation. So what I can do is I can calculate the value of P from this particular equation. That comes out to be C upon V raised to power gamma, and I can say it is equal to V raised to power minus gamma into C. And this I have already told you, this is the ratio of specific heat. Okay, so from this equation, if you will see here, W1 to 2, work transfer for the process 1 to 2 is equal to integral 1 to 2, and pressure is now this value, C over gamma minus C upon V raised to power gamma, or this particular value. So this I have kept here in place of pressure. Okay, so remember this equation so that I can explain it on the next slide. Okay, so what I have done, I have taken, because C is constant, so you can see it here. What was the expression? 1 by 2 C V raised to power minus gamma dV. So C has been taken out of the integration sign in this particular equation. So this is nothing but W1 to 2. Now you can integrate it. So I hope you understand the integration here. When we integrate v raised to our minus gamma, we will have to add plus 1 and divide by the same values. And then these are the limits from 1 to 2. So it is 1 minus gamma. So it has been taken out of the brackets. This is C. And here we get v2 raised to power minus gamma plus 1 minus v1 minus gamma plus 1. And then in the next step, what I have done, I have multiplied this value inside the brackets. So C v2 raised to power minus gamma plus 1 minus C v1 minus gamma plus 1 upon 1 minus gamma. Okay. So this is the reversible adiabatic process, and PV raised to power gamma is equal to constant. That means P1 V1 raised to power gamma is equal to P2 V2 raised to power gamma. So what I have done is, this is the value of C. Okay, this is the value of C. So let us put this value in this particular expression here. Okay, so what is the value of C? Because we are having V2 here in the first term, so I will take in the first term P2 V2 raised to power gamma, and this is V2 raised to power gamma minus 1. So if you take both these V2s, what you are left with? You will be left with only P2 V2. Similarly, in the next term, I am putting C as P1 V1 raised to power gamma multiplied by V1 raised to power minus gamma plus 1. So finally, when I solve this, I will get W1 to 2 is equal to P2 V2 minus P1 V1 over 1 minus gamma. And this is the value P1 V1 minus P2 V2 over gamma minus 1, because now this gamma minus 1 is 1 minus gamma is transformed into gamma minus 1. So the negative sign is taken care of in the numerator here. So the final expression comes out to be P1 V1 minus P2 V2 over gamma minus 1. Okay, so I will end my lecture here. It is already 1:59. So if you have any question, you can ask. Any questions?
No, sir.
No.
No,
So thing is, as you have seen, all these integration means derivations we are doing verbally. So I will be giving this as an assignment. Once again, you will have to submit this class as an assignment. Okay.
Okay, sir.
Okay, sir.
Just wait. I have to take your attendance.